Water vapor in the atmosphere of a super-Earth located in the habitable zone K2-18 is 8 times the mass of Earth, and at the time of its discovery, it was the only planet orbiting a star outside our solar system known to have both water and temperatures that could support life before Hubble. Did this work, only one planetary system had ever been confirmed. Hubble's observations have shown us that planets are forming around more stars than previously thought, raising the possibility that life may exist somewhere out there, and in the future, Hubble may find signs of life. In one of these fingerprints is a prominent international collaboration between NASA and ESA Hubble Space. Telescope will continue to operate as long as its components remain in good working order and provide good service to the scientific community. Its unprecedented capabilities have made Hubble one of the most powerful scientific instruments ever created by man, and certainly the most beloved by the public. How spectroscopy works, and what studying light can reveal about the universe. Astronomers are using D-stellar spectroscopy to study exoplanets in the search for life. This video will explore how spectroscopy works and how it supports valuable research with NASA and ESA Hubble Space Telescope, including groundbreaking studies of exoplanets. While images of the universe excite and inspire the public, spectroscopy is a fundamental tool that astronomers use to study the universe. Hubble's spectrometers provide the data scientists need to analyze the matter that makes up stars, nebulae, galaxies, and atmospheres. The planet's Hubble is equipped with 2 spectrometers. The Space Telescope Imaging Spectrometer, installed in 1997, and the Cosmic Origins Spectrometer, installed in 2009. Any object that absorbs or emits light can be studied using a spectrometer to determine characteristics such as temperature, density, chemical composition, and velocity. As the light travels into the spectrometer, it is separated by a dispersive optical element into different components or wavelengths. For study, this element acts like raindrops, scattering light to form a rainbow. The scattered light is then focused onto a sensor and displayed as a spectrum. Astronomers can analyze the spectral pattern to decipher the atoms and molecules present in the light source. This helps them understand the different physical and chemical properties of that light source. In this way, images from Hubble tell us what an object looks like, while spectral data tells us what it is. What is it made of? The exoplanet spectrum is one of Hubble's most important contributions to astronomy, placed in orbit around the Earth. Hubble is not obstructed by the Earth's atmosphere, which absorbs light from the outside. The telescope is also equipped with sensors sensitive to light from the outside. Spectroscopy has been the basis for many important discoveries from Hubble. For example, Hubble has recorded the signature of a black hole, and its spectral observations have left a mark on the distant universe, using light from quasars to help astronomers study the raw materials that make up galaxies. The spectrum has also become an essential tool in Hubble's study of exoplanets. This is especially significant because when Hubble was launched, planets outside our solar system had not yet been discovered, thanks to its spectrometers. Hubble has provided the first direct detection of the atmosphere of a planet orbiting an extrasolar star, and has detected organic molecules in the atmosphere of a planet. In this way, spectral studies of the atmospheres of exoplanets transiting their host stars have been carried out by astronomers at the Hubble Pioneer. These exoplanets are studied as they pass in front of their host stars, as observed from Earth, as chemicals in their atmospheres leave characteristic traces in the spectrum by filtering out certain wavelengths of starlight. In the search for signs of life, astronomers are looking for characteristic spectral traces. Each chemical element in the atmosphere of an exoplanet will block light from the host star at certain wavelengths, creating absorption lines in the spectrum of the star. This is how astronomers can determine the presence of atoms and molecules. specifically some of which are important prerequisites for life, such as methane, water, oxygen, ozone, and others. For example, during the total lunar eclipse, in January 2019, astronomers used the Hubble to perform a special spectroscopy experiment to test how they will observe Earth-like planets orbiting other stars in the future to search for life. The perfect alignment of our planet with the Sun and Moon during a total lunar eclipse mimicked the geometry of a terrestrial planet passing in front of its host star. In this innovative study, Hubble used the Moon as a mirror to reflect sunlight that had been filtered through the Earth's atmosphere. Spectral observations of this light detected signs of ozone in the Earth's atmosphere, an important prerequisite for the existence and possibly the evolution of life as we know it on Earth to date. Astronomers have used Hubble to observe the atmospheres of gas giant planets as they pass in front of their host planets. However, terrestrial planets are much smaller, and their atmospheres are also thinner. So analyzing these signs is much more difficult, which is why researchers will need much larger space telescopes than Hubble to collect the faint signal. As starlight passes through the atmospheres of these small planets during transits, a larger light-collecting area would allow for more efficient detection of these faint signals. The James Webb Space Telescope, a collaborative effort between NASA, ESA, and CSR. The ability to penetrate deep into the atmosphere of an exoplanet to detect mean and oxygen if they are present not only aids in spectroscopic observations of exoplanets. This new observation also pioneers new spectroscopic studies across all areas of astronomy. Our knowledge of exoplanets has grown rapidly in recent years. Astronomers have discovered numerous worlds beyond our solar system, even deducing information about their sizes, temperatures, and atmospheres. But how can scientists learn these details about planets that exist at such great distances from us? One way scientists do this is by discovering exoplanets from the transit method. Exoplanets raise intriguing questions from the possibility of Earth-like worlds to alien life. But pursuing the answers to these